Good afternoon, engineers. Welcome all the friends for participating in RSM online training course. I'm the host and I'm also the marketing manager of Cinerock. Welcome. I'm glad to have this opportunity to meet so many friends abroad through this online training course, and welcome all the participants for this special course on cross-hole sonic lodging testing. Cross-hole sonic lodging testing method is a relatively mature and accurate pi integrity testing method. It is applicable to the integrity inspection of concrete cast-in-place pipe with embedded acoustic pipe, which is commonly used in field testing at home and abroad. Cross-hole sonic lodging testing method is to evaluate the quantity of concrete and judge the integrity of pipe body through the change of acoustic parameters of sound waves penetrating concrete. That is to say, the integrity of pipe is mainly determined by the corresponding relationship between the acoustic parameters of concrete and the concrete quantity. The purpose of this course is to learn the principle of the sonic lodging testing, understand the relationship between acoustic parameters and concrete quality, and know how to judge the integrity level of pipe body by the parameters and the graphs. In 2008, Cinerock independently developed the RSM SY7 series 4-channel cross-hole sonic lodging tester, realizing the 4-channel testing mode, which can complete the full combination test of 6 sections by 1 lift, greatly improving the detection speed and greatly reducing the work intensity of on-site inspectors. During the lifting process, the test waveform, wave train, wave speed, and wave amplitude and other information of 6 profiles can be clearly observed at the same time. At present, RSM sonic lodging tester have been serialized and applied for relevant patents. RSM SY8 ultrasonic pi integrity CT imaging tester is a breakthrough in introducing tomography technology into the acoustic pi integrity detection by transmission method, and it can cut the tested pi into 18 acoustic measuring lines at one time, and the 2D result can be fitted to 3D pi foundation defect model through our fitting software. The testing result is more intuitive and efficiency. Now, today's course will last about 2 hours, and the course is divided into 4 parts. The first part is to introduce the cross-hole sonic lodging technology. The second part is to introduce the operation process of CSL testing. And the third part is to share some typical cases of common quantity defects. And the last part is to introduce the CT method. Welcome again, all the students. I really hope you can get something from today's course. And now we will enter the formal class. The first course is cross-hole sonic logging technology. And our teacher will introduce the test principle and the test method, explain the relationship between testing parameters and the concrete quantity. This class will last about 30 minutes. If you have any questions through the course, welcome to share your question in the chatting box, and we can have more discussion during the Q&A session after the class. Now the class begins.
Let's first look at Chapter 1, CSL Testing Principles and Methods. If the engineers has not done the test using the ultrasonic transmission method, let's get to know it through these two pictures. On the left is the common use of the acoustic wave transmission method to test the pile foundation. There are 4 acoustic tubes embedded in the pile. Each tube is placed with a sensor, and a tripod is erected. There is an automatic counting device on the tripod, and then the test cable is lifted up at a constant speed to complete the integrity test of the whole pile. Then the picture on the right may be seen less. This is the integrity test of the underground diaphragm wall. This method is used more now. For example, the subway and some large bridge constructions will use the underground diaphragm wall. So the integrity of the underground diaphragm wall needs to be tested. This kind of test is exactly the same as the test of the whole pile, by the acoustic wave transmission method. But the arrangement of the acoustic tube is slightly different. But the principle is the same. Therefore, the acoustic wave transmission method can not only test foundation piles, but also can be used to test underground diaphragm walls. Let's take a look at the basic principles of the acoustic transmission method. After the foundation piles are formed into holes, before pouring concrete, we will pre-embed several acoustic tubes in the piles as channels for the acoustic wave transmitting and receiving transducers. The number of embedded acoustic tubes will have certain requirements in the criterion. When the concrete of the pile body has been poured for several days, the testing is started using the CSL device along the longitudinal axis of the pile at a certain time and interval, point by point, to detect some acoustic parameters of each cross profile of the pile body through which the sonic wave passes. These sampling data are processed, analyzed and judged to determine the position and extent of concrete defects in the pile body. Therefore, the continuity, integrity and uniformity of the concrete can be inferred to evaluate the integrity level of the pile body. So how do we understand the acoustic parameters of each profile of the pile body, the location and extent of defects? We first need to understand why the sonic transmission method can test the defects of the pile. Ultrasonic is a spherical wave. When a spherical wave encounters a defect, it propagates around the defect. Bypassing the defect causes the actual propagation path L of the wave to increase and the time t to increase, while the path of the acoustic tube orifice set by us in advance is unchanged. According to v equals L at t, the calculated velocity v decreases. For the same reason, the actual sonic wave travels a longer distance than the preset distance. The amplitude will gradually decrease with the increase of the propagation distance during the propagation of the medium. So the energy, the amplitude energy, also falls. This is also the principle why the acoustic transmission method can detect defects. When the ultrasonic wave encounters a defect, it will bypass the defect and continue to propagate. The increase of the actual propagation path results in an increase in the detected time, a decrease in the calculated velocity, and a decrease in energy. When this method of testing the integrity of the pile foundation by the acoustic wave transmission method is actually put into use, it is actually the cross-hole sonic logging test in the pile. Transmission means that no matter how many acoustic tubes there is one probe inside each acoustic tube. Ultrasonic waves are emitted by one probe, travel through the concrete to another probe to receive it. This method is called transmission method. The cross-hole transmission method in the pile can be divided into flat measurement, oblique measurement, cross-oblique measurement, fan-shaped measurement and other methods, according to the change of the placement depth of the transducer. When testing, it can be used flexibly according to actual needs. So when are these three methods used? Let's take a look at the cross-hole sonic logging in the pile. First of all, we generally use the flat measurement method for on-site test, and conduct a general survey of each profile to find out the test points with abnormal acoustic parameters. The first method in the principle is the flat measurement. If the flat test is used and it is found there are acoustic anomaly parameters, that is, the pile body is defective, then we will proceed to step 2. There are two methods for step 2. The commonly used method is encrypted flat measurement. That is, the arrangement of encrypted measurement points. For example, a 20 cm testing point is encrypted as a 10 cm testing point. This is helpful for judging the distribution range of defects. Another commonly used method is the oblique measurement method. The oblique measurement method is that two probes are placed at different heights. This method can test the extent of the defect and defects caused by mud-wrapped. The method of fan-shaped scanning is rarely used because the span and energy it tests are uncertain. Let's take a look at the flat measurement. It is to perform synchronous lifting and lowering at the same elevation to complete the testing. Note: the two probes must be on the same level during the flat measurement. Oblique measurement. The transmitting transducer and the receiving transducer are placed at different heights for simultaneous lift, and the abnormal measurement lines of the two acoustic parameters are analyzed to further accurately determine the defect range. Note: there are two sets of tests for the oblique test. In the first set of tests, probe number 2 was positioned higher than probe number 1, resulting in a height difference. In the second set of tests, probe number 2 was positioned lower than probe number 1. The two sets of test signals form the cross-oblique test result. Note: oblique measurement is only that the height of the initial position of the probe is inconsistent, but it is still lifted synchronously, and the height difference remains unchanged during the lifting process. Fan measurement. One probe is fixed at a certain height, the other probe moves point by point, and the testing line is distributed in a fan shape. Note: since the path distance of each testing point in the fan measurement is different, although the velocity can be converted and compared, The measured value of the amplitude is not comparable with each other. In addition to path distance, the amplitude is also related to the azimuth, which is not a linear change. Therefore, it can only be found whether the testing line encounters defects, according to the sudden change of the value of the adjacent test points. This method is actually less used now. The acoustic transmission method for pile foundation integrity test. Using traditional CT testing in the early days, needs to put the probe into the pile body to continuously move up and down to form an array. Collecting data is complex. The outstanding disadvantage is that the sampling speed is very slow, and it takes more than 2 hours to test a pile. The amount of collected data is very large, and the computer with large memory is required for indoor data processing. And the performance requirements of the computer are very high. And the imaging speed is also slow. There is simply no way to get a reference result on site. Later, a new method was researched, which we call new CT testing. The biggest advantage of this new CT testing is that a group of probes is placed in each acoustic tube. The height difference of the transducers in each tube is relatively small, and the attenuation of sonic wave transmission is relatively small. The collected data is of high quality, and the testing time is the same as the sampling time of the conventional flat measurement method. In fact, it has no effect on the field test, and it is enough to lift it once. Therefore, this method has a fast on-site sampling speed, a small amount of data, and a fast imaging speed, which can achieve the effect of real-time imaging in the field. The picture on the far right is the effect of simulating the whole pile with a 3D image after we tested it. The dark blue distribution area is where we calculated that it is a defect. On the left is a traditional CT 2D perspective map, sorted by the size of the velocity. The lower the velocity, the lighter the color. So we can see from this picture that there should be a defect in this area. But it is impossible to see where the defect is, in which acoustic tube, and what is the relationship with the pile. The real CT should be like the picture on the right, 3D. The whole pile model is presented, and the defects at the bottom of the pile and a local defect are displayed very clearly. Therefore, this new CT testing can be said to be the most advanced technology for testing pile foundation integrity by acoustic transmission. After testing, we need to understand the relationship between testing parameters and concrete quality. Let's take a look at why concrete cast-in-place piles are not easy to test. First of all, the construction is difficult. And then the hardening environment and the molding conditions of the concrete are complex. It can be said that what is the biggest challenge in concrete tests so far? There is no model, because each pile is cast in place. There are no two identical leaves in the world. So there are no two identical piles, and each pile is unique. It is easy to produce honeycomb, cracks, mud, porosity, necking and other pile body defects, which will pose a serious threat to the safety and durability of buildings. So on the basis of no model, how can we explore, discuss, and determine this matter? This depends on the level of our testing personnel and testing equipment. This effective method for evaluating the integrity of concrete piles is mainly derived from the nature of ultrasonic waves. Ultrasonic waves propagate through concrete, and its acoustic value changes. Our commonly used acoustic parameters are velocity, amplitude, frequency, and waveform. Note: the waveform is now added to the parameter. The velocity reflects the elastic properties of concrete, and the elastic properties have a certain correlation with the strength of concrete. So there is a certain correlation between the velocity and the strength of concrete. For concrete with the same conditions, the tighter the interior and the lower the porosity, the higher the velocity and the higher the strength. But is this correct? However, it is not advisable to calculate the strength of concrete from the velocity. We cannot say that the higher the velocity, the higher the strength. We can only say that under the same conditions, it is right. The same conditions refer to the same batch number of concrete poured, and the same batch of pouring time. The speed of pulse wave propagation in concrete is also directly related to the density of concrete. Why are our ultrasonic able to detect defects? After the ultrasonic wave encounters a defect during the propagation process, it will propagate around the defect, resulting in a longer actual path and propagation time, resulting in a smaller wave velocity in the calculation result. So this is the principle of ultrasonic test of pile body defects. As long as there are holes or cracks, these defects make the ultrasonic propagation path longer. The tested sound time increases, and the velocity decreases. This is the principle. The same is true for amplitude, which represents a degree of attenuation of energy. If the ultrasonic travels farther with a certain energy, then the energy will be attenuated and will drop. Therefore, the strength of the amplitude is related to the viscoplasticity of the concrete. As long as there is low strength in the concrete, segregation, mud, and honeycomb, the amplitude will decrease significantly. In this method of ultrasonic cross-hole sonic logging, frequency is not the decisive factor. Frequency characterizes the attenuation of the medium. It can only be said qualitatively that when a defect is encountered, the dominant frequency of the received wave is significantly reduced due to severe attenuation. Note: if there is a defect, the frequency will drop, but the specific value of the frequency will be counted as a defect, and there is no specific regulation. Therefore, the frequency cannot be quantified, but can only be used as a reference. So what effect does the waveform have? We can take a look. When passing through the defect, the ultrasonic wave will propagate around the defect, and there will be a phase difference in the sonic path. After superposition, it will interfere with each other, causing the waveform of the received signal to be distorted. The main reason for waveform distortion is that it propagates around the defect, or there is a sound path phase difference with the direct wave signal, which is then superimposed. Let's take a look at a normal waveform. A normal ultrasonic signal should look like this. It has several characteristics. The first feature is that its first wave is relatively steep. The second feature is that the second half of the cycle following the first waveform cycle reaches higher amplitudes. The third feature is that the waveform is not distorted. No distortion means if we connect every peak point of the ultrasonic signal, you will find a very characteristic law. Form a figure like a fish. This is a fairly standard signal. Let's take a look at the problematic defect signal. The first wave is not good. It is gentle, and the amplitude is too small. There is basically no waveform in the subsequent continuous cycles. And there is serious distortion. It should be noted that when the defect is serious, the sonic wave cannot be received. When a defect is large enough, the ultrasonic wave may not be able to bypass the defect, or the attenuation is very severe due to the long stroke after bypassing the defect. So the most serious defect is that there is no way to receive ultrasonic waves. If you want to compare these several acoustic parameters, the test value of velocity is relatively stable, with good repeatability, and is less affected by non-defect factors. The amplitude is more sensitive, and it is another important parameter for judging the quality of concrete. Frequency can only reflect the attenuation of sonic in concrete, thus indirectly reflecting the quality of concrete. The waveform is an important direction to reflect the quality of concrete, and it is more sensitive to the defects inside the concrete. During the on-site testing, attention should be paid to observe the change of the entire receiving waveform as an important reference quantity for comprehensive judgment. Let's look at some of the relationships between common defects and acoustic parameters. The first type of sediment, which generally appears at the bottom of the pile, is a loose medium that attenuates sonic waves very sharply. Both the velocity and the amplitude of sonic drop drastically. The second mixture of silt and grout may be caused by improper pouring and lifting. This condition also results in a significant drop in the velocity and amplitude. The third type of whole wall collapse or mud mass, velocity and amplitude decrease. After encountering a defect, the ultrasonic wave will propagate around the defect. If these defects are small, the sonic will not go around the outside in a large circle, but will propagate along the gap between these defects, with a certain slight change, but it does not affect the whole. Therefore, if it is this very tiny bubble-dense concrete defect, its velocity will obviously not change much. But this bubble-dense concrete has obvious absorption effect on ultrasonic waves. Therefore, once the bubble-dense concrete appears, its velocity does not drop very much, but the amplitude drops sharply. In the process of concrete segregation, there are some places where more mortar is formed, and less coarse aggregate is formed. The velocity mainly depends on the elastic properties, which has a certain relationship with the concrete strength. Therefore, if there is a part of the mortar without concrete, and it is a very dense mortar, due to its uniformity, the energy of the sonic will not be attenuated much during the propagation process. The amplitude is basically the same, and even increased. The velocity has always been a decreasing process, because there is no coarse aggregate in it. as we have said before. The real time of ultrasonic propagation. The real time is equal to the tested time minus the system delay time, minus the error of the acoustic tube and water, correction time. Then L, the inner edge of the acoustic tube, is divided by the real time. Get the velocity. The obtained velocity will also have some errors. The first error arises from the accuracy of the acoustic measurements. Usually, for example, it is less than or equal to 0.1 microseconds. When doing the ultrasonic test, the interval setting of the instrument is 1 microsecond. Then, the accuracy of the time, if a relatively small component is measured, is actually reduced. But it's no problem for testing the integrity of piles. If you use our equipment to test the pile, you can set the sampling interval to 1 microsecond. And the error is 2 to 3 microseconds when judging the position of the first wave. Checking the integrity of the pile body does not have much impact. System measurement error. Whether the correction is reasonable, and whether the measurement of the acoustic tube wall is accurate are the sources of errors. The horizontal position of the transducer is different. What is the horizontal position difference? The transducer will not be completely centered on the acoustic tube throughout the test. In the extreme case, the transducers are all close to the inner wall of the acoustic tube, or close to the outer wall of the acoustic tube, and this extreme error may reach 20 to 30 microseconds. May affect velocity of 300 to 500 meters per second. The vertical positions of the transducers are different, and the transducers in different tubes are not in the same horizontal position. It will cause the propagation path to become longer and the test velocity to decrease. There are also noise interference, first arrival time, etc. If there are large machinery in the surrounding area, you must wait until the construction is completed before testing, because it will affect the first arrival time. Non-parallel of the acoustic tube. Error in span measurement. The measurement of the span has a great influence on our testing results and must be accurate. For amplitude calculation, A is the actual measured voltage, and a 0 is the minimum voltage that can be measured by the instrument. What you get through this formula is dB, and dB is the concept of decibel. There are many sources of error in amplitude. The probe pull-up speed should not be too fast, because the collision of the probe will cause the offset of the baseline. The reversal of the waveform caused by the crack will cause the error of the first wave recognition. The parameters cannot be adjusted during the testing process. PSD can actually be understood as the square of the time difference between two adjacent measuring points, divided by the height difference between the two adjacent measuring points. This is a reference value that acts as a warning and a magnifying glass. Two roles of PSD. 1. A magnifying glass. 2. The main function is to eliminate the influence of non-defects such as tube inclination, non-parallel, and uneven change of concrete. There is no specific criterion for the value of PSD, which can be used as a question area for further detailed testing.
Now the first part of the course is over. We have sent a sign-in link in the chatting box. I see many new comments, and you need to sign in, and we will issue a certificate who have been signing our course. And just to emphasize, sign in means you have been participated in today's course. So if you want to get a certificate, you need to sign in. Now we will have 10 minutes rest. During the rest time, our teacher will answer the questions. If you have any question, you are welcome to have more discussion with our teacher. Okay, after 10 minutes, our class will continue. The next course is on-site teaching of CSL testing, and see you later. Welcome back. Now we will enter the second part of today's course, on-site teaching of CSL testing. In this part, our teacher will introduce the detailed operating steps of CSL testing, including on-site operating, data sampling, and data analysis. If you have any questions during the course, you are welcome to share your question, and we can have more discussion together. Now the class begins.
RSM SY7D 4 channels cross-hole sonic logging tester teaching video. 1. Device description. CSL host, depth counter and connecting cable, pipe orifice pulleys, tripod, plane probe and connecting cable, power adapter, toolkit. 2. Applications. The device is suitable for the integrity test of concrete cast-in-place piles to determine the position, scope, and degree of pile defects. Applicable standards. Standard test method for integrity testing of concrete deep foundation by ultrasonic cross-hole testing. Ultrasonic transmission method refers to transmitting and receiving acoustic waves between the pre-buried acoustic tubes in the pile body through the transducer. Acoustic detectors are used to detect the acoustic parameters of sound waves passing through the cross-section of the pile at a certain interval along the longitudinal axis of the pile. Afterwards, these test data is processed, analyzed, and judged to determine the location, extent of the defects in the concrete pile body, thereby inferring the continuity, integrity, and uniformity of the concrete pile body and assessing the integrity level of the pile body. 3. Operation preparation. 1. Before testing, it is necessary to collect the information and data of the tested project, and the test plan shall be prepared according to the purpose, and the foundation pile information shall be recorded. 2. Before the test, the delay time of the instrument system should be determined by the rate method according to the specification. We can also simply measure the delay time of the instrument system by crossing the acoustic transducers for acquisition. Connect the two transducers to the host, CH1, CH2. Click Ultrasonic Foundation Pile Testing, Settings, Advanced Parameter Settings in turn. Set the parameters such as the pipe outside diameter, pipe inside diameter, and probe outside diameter to the same value, and set the system adjust time to 0 microseconds. Click Save in turn to enter the sampling interface. Cross the two transducers attached to the instrument. Click Sample. After the waveform is stable, read the first arrival time as the system 0 calibration time of the channel and record it. 3. The 4 acoustic tubes are numbered clockwise from a specific orientation. For example, the 4 acoustic tubes can be numbered as A, B, C, and D, respectively. The specific direction can point to the north, or it can be a small mileage to a large mileage direction. 4. Use a Vernet caliper to measure the outer and inner diameters of the acoustic pipe and the outer diameter of the transducer, accurate to the millimeter. Every 2 acoustic pipes form a test profile. Measure the net distance between the outer walls of the acoustic pipes as the profile span, and measure and record one by one with an accuracy of millimeters. 5. Fill the embedded acoustic pipes with water and check whether they are unblocked. 4. On-site operation. 1. Install the depth counter. A stable position should be chosen to erect the tripod to the greatest extent. The bayonet of the depth counter should be installed at a leveled position as much as possible. Install the depth counter and align the 2 vertical spools in the direction of the pile. 2. Lower transducer. Put the 4 transducers into the tubes respectively. Make sure that each transducer reaches the bottom of the tube and keep the cable in a straight state, and record the value on the transducer cable scale as the drop length. Measure the exposed length of the acoustic pipe with an accuracy of millimeters. Confirm whether the drop length of the 4 transducers are the same. If not, find the reason and adjust it. Place the transducer cables in sequence into the trunking of the depth counter. Tighten the transducer cables one by one. 3. Connect to the host. According to the number of the acoustic pipe, connect the transducers in each acoustic pipe to the corresponding channel of the host in turn. Connect 4 transducers to the interfaces with CH1, CH2, CH3, and CH4 respectively, and connect the depth counter connecting cable to the interface with H on the host. Connect the other end of the depth counter connecting cable to the corresponding interface of the depth counter. 4. Start the host. Click Ultrasonic Cross-Hole Test. The main interface is divided into 3 areas, namely Wave Display Area, Waterfall Wave Display Area, and Operation Command Area. 5. Information Input. Click the Setting button and then enter the project name, Save Path. After Save Path setting, the instrument will generate a folder named after the corresponding character. If the project name is not modified, the files of each pile are saved in this folder by default. Set up the on-site parameters in sequence such as pile number, pipe length, testing depth, and pile D. Notably, if there are no special circumstances, it is recommended to set the pile length and the testing depth to be consistent. Set the node spacing, depth record format, angle, and specification information according to standard and site conditions. Input the spans in sequence into the Profile Info section. 6. Host Parameter Settings. Click Advanced Parameter Settings, Device Parameter, according to the accuracy requirements of the testing pile. Generally set the sample interval to 1 microsecond, the sample length to 512, the pulse width to 3, and the transmit mode to be low voltage. When the span exceeds 3 meters, high pressure can also be selected. According to the size of the pulley used, select the corresponding pulley parameters. Generally, the default is the big pulley. If any errors are found during the test, you can click here to improve the accuracy calibration to correct the pulley parameters. Enter the system adjust time of the corresponding profile one by one. The outside and inside diameters of the acoustic pipe measured on site, the probe outside diameter, the pipe WS, and the water WS. The instrument will automatically correct the acoustic pipe, coupled water, and 0 sound. Save and exit. 7. Gain and delay adjustment. Click Sample and adjust the gain and delay according to the size of the collected waveform and the position of the first wave. During the testing process, it can also be adjusted by clicking plus and minus in Auto. The principle of gain adjustment is to make the waveform display amplitude fill the display area as much as possible without causing clipping. The principle of delay adjustment is to make the starting position of the signal within the range of 1/3 to 1/2 of the abscissa until the ideal effect is achieved. You can also choose automatic adjustment in the adjustment interface. The instrument will automatically search for the first wave and set the appropriate gain and delay. If the ideal waveform signal cannot be obtained after multiple adjustments, after eliminating the faults of the instrument and sensor, the transducer should be lifted up to the point without defects and then observe whether the signal can be adjusted ideally. 8. Start test. Click New, enter the file name, and lift the transducer cable at a constant speed until the transducer reaches the nozzle. The current sampling depth is displayed in real time as the transducer is raised. Note that the lifting speed should be controlled within 0.5 meters per second in order to prevent the interface of the waveform caused by the frictional collision of the sensor and the acoustic pipe. The boost speed symbol is green for normal and red for too fast speed and the possibility of missing points. 9. Click Save to complete the test. 5. On-site data analysis. Click File, choose to open the current test file, click Analysis, and observe the depth WS curve, red curve, and depth AMP curve, blue curve, profile by profile. Observe whether there are acoustic anomalous measuring points in each test profile. If it is found that the acoustic parameters are abnormal, the abnormality of the pile should be further confirmed in time, such as encrypted remeasurement and oblique measurement. After on-site sampling and save or analysis, the data could be exported to a U-disk. 6. Precautions. 1. The concrete strength of the tested pile should not be lower than 70% of the design strength, and shall not be lower than 15 megapascals, and the age shall meet the requirements of the standard. 2. The acoustic tube should be closed at the lower end, capped at the upper end, and free of foreign matter in the tube. The acoustic tube should be filled with clean water, and the transducer should be able to rise and fall smoothly in the acoustic tube. 3. The data needs to be recorded clearly during the testing, and the field information must be input in strict accordance with the recorded values and checked on a section-by-section basis. 4. Since the instrument can test multiple profiles at one time, when inputting the span, be sure to pay attention to the corresponding relationship between the instrument channel and the acoustic tube. 5. Testing instruments must be within a valid calibration period. When using testing instruments and supporting equipment, they should be operated in strict accordance with the requirements of the regulations or instruction manuals. Transducers, sensors, and other equipment should be handled with care. 6. In order to protect the connecting wires of transducer well, please put an orifice on each acoustic tube orifice respectively. 7. When testing, make sure that the 4 transducers are bottomed out and on the same level, and that the depth information matches the length of the pile. 8. Avoid tangling of the transducer cable during lifting.
RSM Series Cross-Hole Sonic Logging Tester Introduction. There are 3 models of RSM Series Sonic Logging Testers. RSM SY8C Ultrasonic Pile Integrity CT Imaging Tester. RSM SY7D for Channels Cross-Hole Sonic Logging Tester. RSM SY6C Ultrasonic Pile Integrity Tester. RSM Series Sonic Logging Testers are available in English version, and they are all applicable to American standards ASTM D6760-16. In China, Sinorock is the main editor of technical code for detection of building foundation pile JGJ10620014 and foundation pile cross-hole sonic logging tester DB42AT92320013. The first 4-channel sonic logging tester is designed by Sinorock in 2003, which have applied 9 invention patents in China. The analysis software is also independently developed by Sinorock, which has applied for software copyright. RSM series sonic logging testers have always been in the first place in the market share in China, and our products have won many awards, such as Patent Excellence Award, Science and Technology Progress Award, Invention and Entrepreneurship Award, and so on. RSM SY8C is equipped with 4 one transmitting and dual receiving cross-hole probes, and 4 dual transmitting and dual receiving cross-hole probes, which can complete testing by acoustic pile tomography detection, by transmission method, and acoustic pile integrity detection by transmission method. When using dual transmitting and dual receiving probe, we can get 6 horizontal testing data and 12 oblique testing data by one lift. Defect size, scope, and specific location of the whole pile can be displayed at real time. The automatic counting and lifting device can be connected conveniently and quickly. And the maximum lifting speed can reach 60 mm. Variation of the speed value of the external profile of the pile tested is displayed by using the chromatogram, and then the chromatogram is crimped and connected to form the tubular slice diagram to show the variation trend of the speed value of the pile body vividly. The software can display the three-dimensional low-speed anomalous body diagram, which can intuitively show the location and size range of low-speed anomalous body by the quasi-physical method. The pile can be controlled by the mouse to rotate along random direction, and the positions of pile body can also be arbitrarily enlarged or shrunk to display the anomalous body in a more three-dimensional way. Though speed contour diagram. The software can display the speed contour diagram. That is, the speeds of various profiles measured are displayed in the form of chromatogram. Then the contour line can be drawn to form the speed contour diagram and the range of speed values of various locations of pile body can be displayed specifically. RSM SY8C is a well-designed pile ultrasonic testing instrument that can achieve efficient on-site testing and 3D functions with high efficiency and accuracy. This is a case of engineering measurement. A board cast-in-place pile C30 is 12 meters long and 1200 mm in diameter. Was pre-embedded 3 acoustic tubes. Is tested by the acoustic transmission flat test method and the foundation pile CT method respectively. After analyzing the plat test ADTA, there is severe defect at 4.0-5.5 m. and relative severe defect at 8.2-8.4 m in section AB. Severe defect at 4.0-5.5 m and relative severe defect at 8.2-8.4 m in section AC. Severe defect at 4.0 to 5.5 in section BC. As we can see in the figure, 3D modeling is carried out with CT imaging software, from where the defect and its distribution of the whole body are displayed in 3D, and the defect location and the horizontal distribution are consistent with the flat test result. This pile is classified as Class 4 pile in China. To further verify the defects of the pile, drilling boreholes is used to confirm the integrity. In the borehole cores figures, the core near 5 m has severe defect and the core near 8.2 m has minor defect. It can be verified by the coring results that the ultrasonic CT test results are pretty accurate. RSM SY7D is equipped with 4 1 transmitting and 1 receiving cross-hole probes. For pipes and 6 profiles testing can be completed by 1 lift. It is applicable for acoustic pile integrity detection by transmission method, and it is available in English version. Conforms to American standards ASTM D6760-16. RSMSY7D 4 channels cross-hole sonic logging tester. Adopts new control technology, which has faster transmission and reception speed and higher testing efficiency. for pipes, and 6 profiles can be completed at one time. It is widely used in the domestic market. RSM SY7 Sonic Logging Pile Integrity Tester is used in the pile testing project of Hong Kong's Zhuhai Macau Bridge. Equipped with new universal pipe orifice pulleys, easy to operate. Adopting the enhanced transducer. The first wave energy is greatly upgraded, and the improved automatic interpretation algorithm is matched to make the testing easier and more efficient. The host is equipped with ultra-thin large capacity battery, only 9 mm thick, which can last for more than 10 hours. The battery is designed to be removable, and spare battery can be used on site to ensure uninterrupted operation. The host is made of ABS plus PC high temperature resistant, flame retardant materials, IP65 waterproof and dustproof, and fearless of harsh environments. The host performance is improved, more stable and reliable. Equipped with metal ultra-thin bracket. The surface is matte paint treatment. Adopt non-damping hinge opening and closing. More durable. The host of the equipment adopts industrial capacitive screen, which is very smooth to use and can adapt to strong light environment. Using newly upgraded sampling software, which is more friendly to use. The test waveforms, wave trains, wave speeds, amplitudes, and other information of 6 profiles can be clearly observed in the field at the same time, and the whole pile quality in the testing process can be clear at a glance. The analysis software has simple operation and complete functions. It can switch the display of wave diagram, data table and grayscale image, and the curve display scale can be adjusted at will. It supports different standard interpretation algorithms, and the interpretation is accurate and efficient. It supports the analysis and processing of inclinometer and fan-shaped test data, and has the function of automatic pipe inclination correction. Different specifications can be selected for report output. Various report templates can be supported, and user-defined functions can also be realized. The report export is more convenient and user-friendly. This is a case of highway sonic logging tester. Pile length 133.12 m. Pile diameter 3000 mm. According to the ultrasonic testing of JTG TF8101-2004, there is no abnormal wave velocity and amplitude in the 6 profiles of the 4 pipes, and the integrity of the pile body can be judged as Class 1. Pile length 24 m. Pile diameter 2000 mm. The span of the acoustic tube is 1040 mm, 1640 mm, 1230 mm, 1170 mm, 1620 mm, and 1080 mm. The on-site testing was carried out with the RSM-SY8C ultrasonic pile integrity CT imaging tester. There were 3 profiles at 18.2 m with abnormal wave velocity and amplitude, which were judged as Class 2 according to the specification. RSM SY6C ultrasonic pile integrity tester is the most cost-effective CSL device, which can complete the acoustic pile integrity detection by transmission method, and is compatible with concrete strength detection by ultrasonic rebound combined method, concrete crack depth detection, longitudinal wave velocity test of rock mass in geological investigation, detection of loosened zone of tunnel rock mass, etc. It has the characteristics of small size, light weight, simple operation and easy learning. RSM SY6C Ultrasonic Pile Integrity Tester has 1 transmitting channel, 2 receiving channels. 2 profiles. Data can be completed at one time with the new automatic interpretation function. The first wave acoustic time and the sound amplitude interpretation are more accurate. The depth wave velocity and depth wave amplitude curves are calculated on STI in the real time during the sampling progress. RSM SY6C Ultrasonic Pile Integrity Tester can be used not only for the integrity testing of pile foundations, but also for other tests. The plane probe can be used to detect the concrete strength, the depth of shallow cracks in concrete, the non-dense areas and cavities in concrete, and the quality of concrete joint surfaces. Hole measuring transducer is optional for detecting the wave velocity of rock mass and loose circle of tunnel rock mass, etc. RSM SY6C Ultrasonic Pile Integrity Tester is a portable multifunction sonic logging instrument with 8.4-inch screen, which is very small, light and portable. RSM SY8C is equipped with a total of 9 probes as standard, 1 of which is a spare probe, and 5 universal pulleys are equipped as standard, including a spare part. In addition, it is equipped with a depth counter, tripod and other lifting counting devices, as well as CT software drive for use in CT software analysis. RSM SY7D is equipped with 5 probes as standard, 1 of which is a spare probe, and the universal pulley is equipped with 5 as standard, including a spare part, and is also equipped with depth counter, tripod and other lifting counting devices. RSM SY6C is equipped with 4 probes as standard, 1 of which is a spare probe, and the universal pulley is equipped with 4 as standard, including 1 spare part, 2 plain longitudinal wave probes, and a depth counter, a tripod and other lifting counting devices. If you need to use the hole measuring function, you can choose hole testing transducer. That's all for the introduction of RSM series sonic logging testers. For more information, please log into the official website of Synarock, www.wesem.net. You are also welcome to follow the YouTube and LinkedIn account of Synarock. We will update the project cases and on-site videos.
Now the second part of the course is over. Again, remember to sign in to get a certificate after the course. Now we will have 10 minutes rest. After 10 minutes, our class will continue. During the rest time, if you have any questions, you can discuss with our teacher. And the next course is Common Quantity Defects. We will show some typical project cases to show you the testing results of common quantity results defects. And see you 10 minutes later.
defects are very common in field testing. Then the most troublesome thing for our testing is the pile bottom sediment, which is very difficult to verify. Therefore, our criterions and reports do not require the type of defect. Everyone must pay attention to which has a very important feature, gradual change. Let's take a look at this waterfall. If we connect the positions of the first wave with a line, we will see that this is a relatively gentle arc. Normally, the defect is an abrupt change. Not trending, but sudden. Once there is such a large-scale gradual change of this waterfall signal, we can say that it is likely to be an acoustic tube slope. There are two more common defects in the pile body, mainly segregation and mud inclusion. There are two cases of segregation. The first case is that there is only coarse aggregate and no mortar. As we can see from the picture on the left, it is a relatively broken situation. There is another kind of segregation, which is that there is mortar without coarse aggregate, and the appearance looks complete. However, pressing it, or testing its velocity, you will find that the velocity in this section is very low. The mud inclusive is generally related to water. In many cases, everyone must pay attention to the fact that in river, bridge pile foundations, and areas with abundant groundwater, there is a construction technique. Underwater cast-in-place pile. Underwater cast-in-place piles are particularly prone to mud trapping. This defect of mud inclusion has great damage to the integrity and bearing capacity of the pile, and this defect is very serious. Due to underwater pouring or certain pouring conditions, vertical tube mud wrapped is also prone to occur. Some silt or mud will be wrapped around the outer edge of the pile, and some will be wrapped inside. Some are wrapped around the outside of this pile. Let's take a look at some engineering examples. For sonic transmission, we are used to looking at waterfall map. The first waterfall map is not easy to fake and is more real. Second, if the position of the first wave is judged inaccurately, the graph will not be very accurate. But the waterfall graph will not be affected. The biggest advantage of waterfall map is that they are intuitive. Just need to find difference. Let's take a look at the picture on the left, and we can see the difference intuitively from this picture. These two positions are obviously different from other waterfall maps. This is the characteristic of the acoustic transmission method. The whole pile can be imagined as a curve, an array divided one by one. Then we use a comparative method. If there are some areas that are obviously different from other areas, then these areas are suspected to be defective locations. So we must get used to seeing waterfall maps. Then through this waterfall map, we have seen that the signal in the two profiles is relatively weak, corresponding to the result of coring. There is basically no signal at this position. That is, there is no normal concrete. We must pay attention to one point. We must have a basic concept of the presentation of the acoustic signal. Defects in locations with no signal are generally serious. If there is no problem with the performance of the probe in other areas, and the signal sample is normal, the position of this signal distortion suddenly appears, then the pile must be defective. This is a typical pile bottom sediment. Sediment is some impurities at the bottom of the pile that cannot be recycled during the construction. or is replaced by other pouring processes. We call it sediment. After pouring the concrete, look at this waterfall again. It is obvious that the waveform in the lower left receded, and the signal has receded to indicate that the propagation time of the ultrasonic wave has increased, and the velocity has decreased. With this typical drop in the velocity, the coarse aggregate at this location must be insufficient and problematic. By taking the core, we can also see that it is no longer concrete. Let's continue to look at the example below. This case is a bit difficult. There is no valid signal in this part of the pile, which means that there must be a problem with the pile. The results of the excavation also showed that there was indeed a problem. This is the 1:2 profile. This is the 1:3 profile. This is the 2:3 profile. There are several acoustic tubes in this picture. Through this waterfall map and the position of the acoustic tube on the right, can you confirm which acoustic tube is the number 1 tube? Which is the number 2 tube, and which is the number 3 tube? With this signal, you should know what's going on at the site. The degree of signal distortion has a certain relationship with the severity of the defect. The greater the degree of distortion, the greater the defect. The signal on the left, 1:2 profile, is the best. The signal 1:3 profile is the second best. And the signal 2:3 profile is the worst. From the picture on the right, it can be clearly seen that the signal in the upper right corner is the best. So this profile is a 1:2. The second best signal is the following profile. This profile has a mud-wrapped tube. And this profile is a 1:3. So the bottom right corner is the number 1 tube. The worst signal is the 2:3 profile. So the lower left corner is tube 3 and the upper left corner is tube 2. Coring needs to be cautious. If the evaluation confirms that the core needs to be taken, it needs to be analyzed and judged to select a suitable location. Waterfall maps can represent a wealth of information on site. As long as you understand the basic principles of the acoustic transmission method. The degree of signal distortion. The most serious is no signal. The second most serious is the faint signal. And the least serious is that the velocity and amplitude have decreased. But the decrease is not serious. Look at this pile. This range, the signal of the waterfall map at this position is basically very weak. From the results of our coring, there are also serious defects. So let's see if this core sample is serious. From this signal, we can clearly see that the velocity or amplitude has decreased to a certain extent. But it is not serious. And the signal is faintly visible. Then it proves the point we just said. The more serious the waveform distortion, the greater the signal attenuation. And even if there is no signal, the defect is serious. Once there is a signal, and it is only slightly attenuated, then the core may be such a local segregation. This defect is not particularly serious. Let's look at the situation of mud on the top of the pile. In the waterfall, part of the top of the pile is still different. Looking at this picture again, there is obvious waveform distortion at this position, which corresponds to this coring part. The worse the signal is, the worse the core sample is. The core is basically the sediment layer, which is also a serious defect. There may be some brief comparisons here. Usually there are piles that can do both low strain and ultrasonic. There is a small co-reflection in this place. which is a defect and is a type 2 pile. From the point of view of the sonic transmission method, this is a type 3 pile. There are also large scales like this. If this is a wrapping defect, it cannot be drilled and cored. So how to judge such a pile? For example, this is profile 1 to 2, this is profile 1 to 3.